This is Bob McFetrich with Beckwith Electric Company, and I would like to thank you again for downloading another session of our integrated Volt-VAr control series. This session, session 6, will be a three-part session. The topic is coordinating an architecture without communications. So in this session, we're going to look at how we would implement an IVVC system in which we were not going to make communications the backbone of the system. Session 1, or part 1 of this session, is going to deal with the basic theory. Part 2 will show a utility example of a large investor-owned utility in the Southeast who's already implemented this type of architecture. And then Part 3 will go through some of the new technologies that had to be designed as the architecture was implemented. So we'll talk about some of the issues that they had come up and some of the features that had to be altered in order to make this a successful implementation. So starting with session number 1, or part number 1 of the session, we're going to just go over the general concepts again. And that is that the voltage is going to drop along the circuit due to losses from load current flowing through the impedance of the circuit and the transformers and so forth. And reactive impedances are much greater than resistive impedances on the distribution system, and therefore your reactive current flow will cause a greater voltage drop than your real current flow. And we realize that we have to maintain the voltage between predefined levels. So we have a low level and a high level, and every customer across that entire circuit must be within those levels. And if we can run the voltage at a lower level, we will reduce the load current and therefore reduce the losses and the voltage drop also. And as a last concept, switch capacitor banks are typically less expensive to install and also for long-term maintenance than our line regulators. And they have the added advantage, besides regulating the voltage, of also being able to supply reactive current closer to the load, so that reactive current doesn't have to flow through as much of the impedance, and therefore we won't see as much voltage drop. So to reiterate this concept, this is a voltage profile of a typical distribution circuit if the only correcting was at the substation level. So if we had no downline regulators or we had no downline capacitor banks, this is how the circuit would look. Now, if we were to add a capacitor bank near the end of the circuit, when that bank closes, we can see that it lifts the voltage at that point up and also on both sides of it. And if we were to add a second capacitor bank to the circuit, we would see now that we've lifted the voltage up at two different places along the circuit. And notice now that we have what's known as a flatter profile. In other words, the delta voltage, or the amount of drop from the low point down here to the high point, is much greater prior to using the capacitor banks than it is after. After, the low point is probably right about here, the high point's about here, so you can see that that's a much smaller delta voltage change from the top of the circuit to the high voltage to the low voltage. And by flattening that profile, what that would allow us to do is to lower the voltage across the entire circuit. So right now, if our voltage profile looked like this, we could shift the entire voltage down when we needed to without undervoltaging any of the end customers, and by doing so we would reduce load. And that is the overall goal of an integrated Volt-VAR control system, is to manage both the voltage and the reactive power. And so you can see that, especially where all the load is, on any given circuit, remember that the majority of the current is flowing here, because as customers come off, down below we'll have fewer and fewer load currents, to where when we get at the end of the line, that's where our least amount of load is. And by reducing the voltage, we're going to reduce the load. With that in mind, we really want the voltage to be lowest at the source where all the load is to benefit the most from those savings. Having the voltage lower at the end of the line really does us no good because the load we're saving on is insignificant. So the only way to get the voltage to be lower here is to make sure that the voltage here is at the low end of the overall voltage. And that's what was accomplished with the capacitor banks. So if we go back and look, before the capacitor banks, our low voltage was at the end of the line, and that forces the front end to have to run high to keep the end of the line voltage above this level. But by adding the capacitor banks, we've now made the end of line voltage not be the lowest voltage on the circuit, but actually the lowest voltage of the circuit is closer to the source. And therefore that would allow us to shift the source down lower, and the lower voltage at the front end where all the current flow is going to give us the maximum amount of benefit when we reduce the voltage. One of the trends has been to have end-of-line monitoring. I've never really understood that, because if the system is designed correctly, the voltage at the end of the line should not be the lowest voltage. If you're monitoring the end-of-line voltage, assuming it's the lowest voltage, you've already failed in your attempt to do IVVC, because for the maximum benefit, we have to have the lowest voltage near the source, not at the end of the line. So if I were to do any monitoring, I would want the monitoring to be somewhere in this first quadrant of the circuit, because that's where we're going to anticipate the lowest voltage with the use of our capacitor banks. So the capacitor banks are used for two purposes in this architecture. One, to reduce the VAR flow through the circuit. So if I've got load here requiring capacitive current, instead of having it come from the substation and have to flow the whole way down to that load, now this capacitor bank can source that current, and we've reduced the amount of VAR current flowing again at the front end of the circuit, and that will reduce the voltage drop. So the capacitor banks are reducing the VAR current, getting us closer to unity or even slightly leading power factor, and then flattening out the profile. And once we have the profile flat, then we can bring in our regulator controls and have them go into voltage reduction when we need to conserve voltage. So the capacitor controls are trying to control the cap banks in such a way that we flatten out the voltage and not go too far leading, and then the regulator control or LTC control will then be responsible for shifting that voltage once we have a flatter profile. One other comment to make here is that one of the trends is for utilities to start to want to run slightly leading on their distribution systems. In previous years, most utilities' goals were to be somewhere between 0.96 and lag and unity. But nowadays, many utilities want to go slightly leading at the distribution bus level, because the transmission and distribution transformer will have a reactive impedance. And if I'm 0.99, 0.98 lead at the substation and I'm pushing a few VARs back in, those VARs will cancel out the impedance of the transformers, and I will be VAR neutral to the transmission system. So, with that in mind, for this type of system to work, we're going to need regulation inside the substation. We can use LTCs, but it's really recommended to go with feeder regulators. We can go with LTCs as long as the load between the phases is fairly balanced, and as long as we fairly balance out the line losses in each of the circuits. But again, on any of these systems, feeder regulation will give us a better resolution, because we'll be looking at each feeder as an individual zone, as opposed to LTCs where we're looking at each bus as an individual zone. The bigger the zone, the harder it is to coordinate. So, if the voltage drop gets too great, we may also need downline regulators. Now, if we do need downline regulators, we would typically place them, if it's one set, about 3/8 of the line length down the circuit. And that's again because the majority of the load is in the front end of the circuit, and therefore we're going to have more losses in the front end than the back end. You wouldn't want to put it halfway down unless you knew that your load center was more heavily weighted at the end of the circuit. But if it's an evenly balanced loaded circuit, then typically you would want the regulator about 3/8 of the way down, because that's where the halfway load point would typically be. But that's what you're looking for, is where on that circuit you anticipate the halfway load point to be. If you apply two sets of regulators, typically they'd be about 20% and 50%. Now, if we do have line regulators, the first thing we're going to have to do is coordinate the LTC or the feeder regulation at the substation with the downline regulators. And the reason we need to do the coordination is going to be shown here. So again, remember that regulators are unidirectional, which means that only the voltage on the load side of the regulator is changed by the regulator. The voltage on the source side of the regulator is not affected when the regulator operates. So if we have this entire circuit experiencing a low voltage, and we were to allow regulator 2 to have the first shot at correcting that voltage, when it raises the voltage, it will only raise this portion of the voltage, its load side. Its source side will not be affected, and therefore this portion of the circuit is still low. That will require this regulator to still raise that portion of the circuit. But when it raises the voltage, notice that it is impacting everything downstream from it, including the voltage on the load side of regulator 2. This may cause this voltage now to go too high, in which case regulator 2 would have to send a lower to bring it back into band. So in this case, by allowing regulator 2 to have the first shot at fixing the voltage, we have incurred 3 operations between the 2 regulators to get this voltage back into band. Where if we would have allowed regulator 1 to operate first, we would have only had the 1 operation. So that is the reason we need to coordinate our time delays with our regulators and LTCs, is to reduce the number of operations of equipment. So, in summary for regulators and LTCs, we are going to possibly need additional regulators outside the fence for long circuits. When we do that, then we have to coordinate the regulators back with the upstream. And the general rule of thumb is you want the regulation closest to the source to have the shortest time delays. And then you want to extend the time delays as you go down line by about 15 seconds. And typically we want the time delays inside the fence to be starting at about 90 seconds because we want to allow the capacitor bank's time to operate first. So if we were to have our LTC or our feeder regulator set at 90 seconds and we had 2 sets of downline regulators, the downline regulators closest to the source would then be at 105 seconds, and the set furthest away would be at 120 seconds. So, again, we want to delay our time delays. Most utilities typically set their time delays on their LTCs between 30 and 60 seconds. And the disadvantage of this is even if you have downline voltage controlled capacitor banks, typically with these short time delays, the LTC will time out before the cat bank will, and you will increase the number of operations on your LTC, and at the same time you'll correct the voltage so that the cat bank will not be able to come in and supply the VAR support it also needs for power factor correction. So whenever you're coordinating LTCs and regulators with capacitor banks, you always want to allow enough time for the capacitor banks to operate first. So therefore, we recommend stretching out the time delays and having a minimum setting of 90 seconds. I know some utilities that go 180 seconds on their time delays at the LTCs. The advantage being that we will have more capacitor bank operations and fewer LTC operations, and also have a better overall power factor. The other thing we're going to look at is now we need to coordinate our regulators and our LTCs again with capacitor banks. And so the first phase of that is to have a longer time delay to allow the banks to operate. But we need to make sure that we don't have too many banks operating. We do want to see a slightly leading power factor, but we've got to remember that too much leading VAR current is just as bad as too much lagging VAR current. So VAR current flowing back through from capacitor banks back to the source is going to create just as much voltage drop across the circuit as it would going from the source to the load. So we need a way to make sure that we don't allow too many capacitor banks to close as the voltage needs to be raised. And the way we're going to do that traditionally is by using the line drop setting, and especially the reactive portion. So we're not going to use the X for regular line drop. We're going to use it to coordinate with our capacitor banks. Now, we're not going to use the R for coordination with capacitor banks, so if you're using R for regular line drop compensation, you can continue to do that if you desire. But again, it makes it a little harder to coordinate because we're trying to get our band centers on our regulators and our capacitor banks to be the same, so that when the voltage is at a certain level, the cap banks and regs are timing, but the caps will beat it. So if we apply an R, we're biasing the voltage at the source and therefore biasing the band center. So our recommendation is in this type of architecture not to use the R at all. But the X is going to be used, but not is we're going to have what we call a negative reactance setting. So first of all, what is negative reactance? Well, if the regulator or LTC control sees negative VARs, what that means is VARs are flowing into the load side of that regulator or the LTC instead of flowing out of the load side, which is another way of saying you have leading VARs. And if we were to put in a negative X for the line drop, and it saw leading VARs, that would induce the LTC or regulator control to bias its band center upward to encourage it to raise the voltage, which then in turn, since we have voltage control capacitor banks, should induce one or two capacitor banks to go off. So the general concept of this philosophy is we're going to have our regulators and our capacitor banks have similar band center bandwidth controls. They're all going to be looking at voltage, but the time delays will be set so that the capacitor banks are always shorter than the regulators and the LTCs. So that if a voltage needs to be raised or lowered, the capacitor banks will always be the first to operate. Now, if the voltage needs to be raised and we get too many capacitor banks closing and we go too far leading, then we're going to have the negative X in the line drop force the regulator or the LTC to raise the voltage to induce one or two of the capacitor banks to come off so that we get back to closer to a unity power factor. So, with that in mind, we need to quickly talk about switched capacitor banks and how we're going to coordinate them. Now, we said with regulators, we want the regulator closest to the source to be the first to operate. With capacitor banks, it's exactly the opposite. We want the capacitor bank furthest from the source to be the first to operate. And the reason for that mainly is the effect the capacitor bank has on the voltage is proportional to the size of the bank and the distance back to the source. So if we have multiple banks and they're all the same size, let's say 600 kVAR, the bank furthest from the source will have a greater effect on the secondary voltage than a bank closer to the source. So the general rule of thumb is we want the bank furthest from the source to be the first one to close and the last one to open. Likewise, we would like the bank closest to the source to be the last one to close, but the first one to open. So, with that in mind, we're going to coordinate, and to do this, it's most easily coordinatable if we have the voltage be the source for the capacitor bank control. So we would recommend it for the cap bank controls to go with a voltage source. Besides it being easier to coordinate with our regulators and our LTCs, it'll also be less expensive for the control. Less expensive because we will reduce the need for line post sensors. Less expensive because we will be hanging less things on the pole. And we can now place the capacitor on any pole we want, even if it's a lateral tap. With VAR controls or current controls, you've got to remember that the control's only going to measure what's flowing through at that point. So if you place the capacitor on a tap, we're only going to be measuring the current or the loading off of that tap instead of off of the entire circuit. But with voltage, we don't have that concern. Finally, a voltage control will work better in reverse power direction. We're going to talk about that in the last of our 3 parts of this session. But we want to engineer an architecture that not only works with the normal configurations of circuits, but with all the new advances in distribution automation and automatic sectionalizing and restoration. We want to make sure that if we tie circuits differently out in the field, that we maintain our coordination and we maintain our benefit and our ability to both have unity power factor on each circuit and be able to reduce the voltage on each circuit. And so with VAR controls, it's very difficult to get them to work correctly in a reverse power mode. So with that in mind, we're going to be talking about voltage capacitor banks. The next thing we have to decide is how to determine how many banks and the size of each bank. So starting with the size of each bank, our goal is to reduce, one of our primary goals is to reduce the number of operations on an LTC or a regulator. One thing that we've got to do to meet that goal is we've got to make sure that if a cap bank operates, the effect it has on the secondary voltage will not be great enough to force a regulator or an LTC out of band. So for instance, if I close in a cap bank control and it affects the secondary voltage by 4 volts, that may induce the regulator or LTC upstream to have to go in the opposite direction to eliminate some of that voltage increase. So as a typical rule of thumb, we'd like to see the effect of any bank be less than 2 volts. So we want to be fine-tuning just like a regulator. So one of the goals here is to reduce single-phase line regulators with capacitor banks, switch capacitor banks, because switch cap banks are much less expensive and much easier to maintain. So with a regulator, we know we've got 16 taps plus or minus and 10% regulation total. We want to try to get close to that with cap banks, and therefore we want to have more smaller cap banks. And we need to protect against the hunting on the LTCs or the regs. Therefore, typical sizes recommended for a 12 kV voltage, it's recommended that we do not exceed 600 kVAR. And for 25 kV, it's recommended that we do not exceed 1200 kVAR. But the general rule of thumb is we want to try to keep the delta voltages between 1 and 2 volts per bank. So now we've got to determine how many banks. And the way we're going to do that typically is we're going to start by determining the total amount of capacitance required on the circuit. And by looking at historical data, we can look at our loading on any given circuit, see what the worst case VAR requirements are, and then add an additional 10 to 15% for load growth. And that will determine the total amount of capacitance we need on any given circuit. Now, once we know that, we need to figure out how much of that capacitance is going to be fixed and how much is going to be switched. There are some utilities that are replacing every fixed bank with a switched bank and making all banks switchable. And that is a viable thing to do, but a lot of times it's not necessarily required. So fixed banks do have the advantage that they're less expensive because we don't need a control or a PT. All we've got is fuses that'll bring the bank in or out, and typically they're going to be left in at all times. So we know that even with no load on our circuits, we will have an impedance that is inductive due to the transformers and due to the cable. And therefore, we are going to need some capacitance to offset that. We also know that our system never has no load on it. So what we're going to do is we're going to look at the lowest load point traditionally on any given circuit, see what the VAR requirements are at that point, and that's the size or the amount of fixed capacitance we need. Once we know the amount of fixed and we know the total, the difference obviously is going to be made up with switched banks. And we already have determined the bank size. Therefore, once we know how many switched VARs we need total, we can divide that by the bank size, round up, and that'll tell us the total number of switched capacitor banks that will be required on any given circuit. Once we know that, then with a fixed bank, the placement would typically be halfway down the line length. And if we're going to require two fixed banks, then it would be 1/3 and 2/3. So if I need one 600 or 900 kVAR fixed bank, because my no-load VARs are, say, 800, so I'm going to put in one 900 kVAR cap bank, I would put that halfway down the line circuit, distance-wise. If I wanted to split that up into two 450s, then I would go 1/3 and 2/3 line length placements with those two fixed banks. For the switched banks, we're just going to take the total number of switched banks that are going to be applied and kind of space them evenly throughout the system. So if I had a circuit that was going to require 5 switched capacitor banks, I would put them at 20, 40, 60, 80, and then near the end of the line. So we're just going to take our line and divide it up into equal segments, and that's where we're going to place our switched capacitor. So now the settings for the voltage controls. So obviously for capacitor banks, we said that we want the cap bank furthest to be the first to close and the last to open. Therefore, we need to have two separate time delays, one for open and one for close. And we also want the time delays on our caps to be shorter than our regs. So typically we would start at the end of the circuit with our close time delays and make the cap bank furthest away be 30 seconds and then add 5 to 10 seconds per bank coming back towards the source. So if I had 3 switched banks, the one furthest away close time delay would be set at 30 seconds, the middle one would be set at 35 seconds, and the one closest to the source would be set at 40 seconds. The opens would be done exactly the opposite. So for the opens, the one at the end of the line would be 40 seconds, the one in the middle would be 35, and the one closest to the source would be 30. We would want our band centers or our limits to be set at the band edges of the regulator. So if my regulator is set with a band center of 122 and a bandwidth of 2, that means 121 is when it's going to want to raise, so that's the voltage level we want to close our cap bank at. 123 is where it's going to want to lower, so that's the voltage level we would want to open. But we've also got to be remembering that our bandwidth has to be at least 1.5 times bigger than the delta voltage on the bank. Again, the delta voltage of a bank is the effect that it has when it operates. And if we get the bandwidth smaller than the delta voltage, we could have a capacitor bank that's locked out and never does operate. We also want to set limits on the cap banks, and we want to make sure that any emergency voltage limits are set such that we keep that same coordination. So again, if I've got a limit a low voltage limit that's going to want a cap bank to close, I want the cap bank furthest to be the first to close. And I don't want them all to close at the same time on a limit, because then I can get into a hunting where I go the opposite direction. So our limits have to be time delay coordinated just like the regular operation, and it's got to be done in the same order. So on a high voltage limit, the bank closest to the source will be the first one to open. And on a low voltage limit, the bank furthest from the source will be the first one to close. We should also make sure that our voltage levels are set to trip at the lightly loaded time of the day, whatever that voltage is when it's lightly loaded. Because if we don't, the bank will never operate. So if we set our open voltage higher than the lowest voltage it's ever going to see, then we're never going to have a bank close or open. So we got to maintain, we got to look at our voltages at the full load voltage, what's the voltage we anticipate, and at the lightly loaded, what's the voltage we anticipate at the location of the bank, and we got to make sure we keep that coordinate. So to summarize, we're going to show an example circuit. In this particular circuit, we have a feeder regulator at the substation, and we have one set of downline regulators. So this will be our first coordination issue, is we would like to set this feeder regulator to at least 90 seconds time delay, and therefore the line regulator would be set at 105 seconds. The next thing is we're going to start at the end of the circuit, and we're going to coordinate these capacitor banks back to their closest regulating device, which would be this regulator. So in this case, we have 3 switch capacitor banks. This one would be set for close at 30 seconds, close at 35 or 40. Maybe we'll go 40, and this one will close at 50. This one will be set for its open to be at 30. This one's open time delay will be 40, and this one's open time delay will be 50. So that we're coordinating the time delays of the capacitors so that the one furthest away from the regulating source, in this case the line regulator, will be set to the shortest close time delay and the longest open time delay. And we will set a negative reactance, typically around 4 to 6, to regulate the power factor and make sure that if we go too far leading on this section of circuit, that we will actually induce this regulator to raise the voltage. And in that case, once we raise the voltage, we'll induce one of these capacitor banks, hopefully the one closest, to open to bring that power factor back down to unity. Likewise, on this section of circuit, we need to coordinate. This is a fixed bank, so there's no coordination with it. We only have the one switch bank, so we would coordinate its time delay with this regulator. And again, we would coordinate with a negative X for the VAR flow. So that is typically how we would coordinate the settings on any given feeder. So in summary, if we're going to go with an IVVC system with no communications to the downstream devices, the first thing we're going to do is we're going to have the cap banks have the first shot at correcting the voltage. So we want our capacitor banks and our regulators to be timing at the same time, but we want the capacitor banks to always have a shorter time delay, and therefore they will always be the first to correct the voltage, and hopefully we're going to reduce the number of operations on our regulators and our LTCs. We want the cap banks, though, when they do correct the voltage, to be coordinated in such a way that the cap bank closest is the last one to close and the first one to open, because it has the least impact on the voltage. We want to keep that end of line voltage up so we can flatten the profile out. So we want to start by getting the voltage up at the end of the line and raising it towards the front end of the circuit. We also are going to coordinate our regulating devices with our capacitor banks in the case that we get too many capacitor banks on, correcting the voltage and driving us into too far of a leading condition. In that case, a negative X setting in the line drop will induce the regulator or the LTC to raise the voltage, therefore inducing one or more capacitor banks to open. But we do have to be careful of one thing in this architecture, and that is if we have too few capacitor banks. If we have too many, we have accommodated that with the negative X. But what is not seen in that is the implicit if we go lagging VARs. So for leading VARs, the negative X is going to want us to raise the voltage to induce the cap banks to go off. But for lagging VARs, it actually induces the regulating device to lower the voltage to encourage cap banks to come on, which is what we would like to do, but we're making an assumption that there are more cap banks to come on. If we either do not have enough capacitance on a given circuit, or we have capacitor banks that are out of service, then we can run into a case where we've got lagging VARs, the LTC or regulating device is lowering the voltage to try to bring more VARs on, and we can risk an undervoltage circuit, especially near the end of each line. So that is one disadvantage, and we're going to correct that in part 3. But if we're implementing it just the way described here using the negative X, the disadvantage is if we go lagging, and the further lagging we go, the more the voltage will be reduced because there's no cap on it. So if we use a 4 or a 6, it's going to keep applying more compensation the further we go lagging. So if we get a circuit that's 0.8, 0.85 lagging, we would definitely not want to employ this type of system. So we've got to make sure that it's engineered such that we have enough capacitors to bring online. So that is session 6, part 1. I hope that you'll join us for session 6, part 2, in which we're just going to go through a utility example and how they deployed this and some of the issues that they ran into. And then in part 3, we're going to discuss some of the new features that were developed to counteract some of the problems that they incurred. So again, we thank your time. We appreciate your support. And if you have any questions, please feel free to submit them to the website or contact any one of your regional salespeople or myself at Beckwith Electric. Thank you and have a blessed day.